Okay, so we start from our second part today lecture. So don't forget next week we have a homework one presentation. So today I just briefly review what I did before is a sound localization. So later on I will give you the upload the paper. We published paper before. That one we use work for hearing aid system. So with 3D sound localization. So what we based on idea is based on TDA, time delay arrival. So this kind of technique we call the TDA. So we are assume the guy wear microphone array in front of their chest. So there will be have a there will be some like a ear aid system. So you'll be make some they have a perception ear perception problem there. So we try to help correct their what their hearing capability. So this one is more like a 3D sound. We are using head related transfer function here. And then what we're talking about is more like how to localize the sound localization based on time delay issue. So according to figure 3, what we divide, we are come out alpha theta phi. So there's no derivation in this paper. So today I already do some derivation for your reference. So, however, some symbol could be plus and minus. That depend that depend on which one is more because we are assume D1 is bigger than D2, bigger than D3, bigger than D4. So here we are trying to, but this one could be different assumption. So they have some minus and plus different, a little bit different. So, but the normal formally the equation could be the same. So the other one, this one just say why we did it here and related to your sampling rate. So we try to calculate correlation. So you can see we have a correlation, try to get a delay, try to get the argument maxima. Based on the argument maxima, we can get a tau, and then we have a sampling rate, and then we can get a delay here. So we have a delay, so we can calculate the 3D. 3D sound is another issue. It's not what we're talking about here. So we have a theta phi, so you can see what we did experiment. So we have an ideal value, and then we have a measurement value, and then if we have an upsample or no upsample, what's the difference here? So this one I will give you later. So though here is like look like if your microphone array is bigger, so their resolution will be better. If the microphone array is too small, so you'll be a little bit confused. The deviation will be larger. So you can see our microphone array is become the square bigger. The H length is bigger, so can make the resolution deviation smaller. So you can see they can get a better performance. Some is somehow. So sometimes could be a little bit different. So this one just show you some what we did before, but we are not focused just on sound localization. They are just focused on hearing aid. However, before we did this one, we also consider sound localization. Try to identify sound location. Based on sound location, we can do the head-related transfer function to try to enhance perception localization. So we are based on head-related transfer function to do it. So this one is what we published. It could be 10 years ago. This one I remember should be 10 years ago. I'm not sure what's the year. Do they have? No. This one should be published by 10 years ago. So go back to your homework one. So you have to double check what's the methodology they are using. So most of them, if you are in time domain, they will be based on time delay. and then based on correlation, in frequency domain could be the phase, because in time domain is time delay, sample delay, but in frequency domain will be transfer to frequency domain will be the phase. So you have to double check. So later on in your paper could be in different way. So try to understand what they say and then give a good report on your homework one. Okay, so we go back to uh, our textbook. So because in the beginning we are talking about the speech signal, so we are not wait for uh, the human being to finish the talk. So we have to partition one frame by one frame. So how to partition? So we are talking about how to do the partition. So the main idea is more like a windowing. So windowing. So you can see there are many windowing, like a rectangular, Bartley, Hamming, and Henning window. So we are trying to find the fast windowing. So you can see their time domain the waveform. So more like a waveform like this one. So rectangular would be more like a try to remove out of the window, become the zero. In the inside the window, keep everything. So the other filter is look like we try to make the boundary symbol, boundary signal become smaller, and in the middle, the signal try to keep original signal as possible. So make it try to keep the original signal. So you can see here what's their frequency response according so many filters. So you can see is a like a rectangular window. So they have a good resolution. So however, the leakage will be larger. Sometimes you cannot catch an idea. Later I'll be give you the example why their performance maybe is not good. So based on we have the other five filter. So you can see Hamming window. So they are main envelope and side envelope. They are deviation bigger than larger than 40 dB. And then the main envelope resolution is okay, not too big. So you can see like a Hamming window, but the leakage is larger than Hamming window. So you can see most of speech processing, they are trying to do the windowing. Most of them, they are using Hamming window. Why they are using Hamming window? So right now you have to know the reason. In addition, maybe the other application, if they are trying to do the windowing, try to make sure minimize the blocking effect. So sometimes most of them will be considered Hamming window. Okay, so speech signal, they're talking about a former. Former is more like a envelope pick. What's the former? What they want to say? Okay, okay, so they are trying to go down to the other figure. Okay, so they give you the idea this bigger, maybe too big and maybe small. Okay, one more. So you can see here, we have using the two windows. One is rectangular window. The other is a Hamming window. So you can see rectangular window try to keep original signal and smooth zero out outside the window. And so inside the window they keep everything there. If we are using Hamming window, they try to smooth it, make the boundary signal become smaller. Boundary signal becomes smaller. So after Fourier transform, so you can see their frequency response a little bit more detailed here. And if you are like you are using Hamming window, so they try to get some more envelope shape. Some frequency response, not too much, so many detail there. So right now they call the formant. What's the formant? I will show you the formant defined. So we call the formant. In the paper, they're talking about the formant here. Harmonic peak at multiple fundamental. So, however, harmonic peak at multiple fundamental frequency are narrow and sharp in the rectangular window speech. So you can see B and D, the formant speech signal structure includes strong first formant peak around 500 Hz, and three border of peak point will be 1350 Hz and 2300 and 3400. So you can see as well. So what's the meaning here? Wait a minute. So there's one. What they're talking in the top. Okay, the window size here is 227. 220 sample here. So you can see here. So what's the formant here? So what we say that what they're talking about the formant. So it's not a fundamental frequency. They call the formant. So you have to know what's the fundamental frequency. So fundamental frequency is corresponding your pitch. Corresponding your pitch. And then if you have a speech signal, like this one, so if we are doing the windowing, so could be not it's too narrow. So I try to make it big. Okay, so in the frequency domain, the pitch. So this one is your fundamental frequency. So you have a like this one and like this one, like this one. So this one is your fundamental frequency. So you have a fundamental frequency. This one your space delta f. So this one is the frequency domain. So you have a pitch here, time domain to frequency domain is your harmonic fundamental frequency. What's the formant? Formant is look like you have a frequency domain. We can see the envelope shape. So this one is your formant 1. This one is your formant 2. This one is your formant 3, and this one will be your formant 4. So you're talking about this formant 1 is around 500 megahertz. This one is close to the 1050. So 350. This one is 2300 hertz. And this one will be 300. Why we are talking about the formant? Because the formant here, what we call the formant in the traditional, we call the speech spectrum. They are from the speech processing. They are considered for speech recognition. They do the speech recognition. So, or speech understanding. They are talking about try to see what's the formant 1, formant 2, and formant 3, and formant 4, what kind of frequency they are located. Based on the frequency located, we try to make sure what kind of pronunciation they are using, like R, E, U, A, O. So they try to know what's the fundamental phoneme. So fundamental phoneme will be based on, we try to recognize your phoneme. So basic sound. We try to recognize your basic sound. So we try to recognize your basic sound. So we have to know what's your formant 1, formant 2, formant 3, formant 4. this one is from the language point of view, because they try to understand what you're talking about the phonics. So some of the traditional to understand, we have a speech spectrum. They call the speech spectrum. They call this one speech spectrum. So most of them, they are considered speech spectrum, and then they try to understand your formal 1, formal 2, formal 3, formal 4. We are not cannot see the more detail. Your envelope shape, we just pick up the pick point, try to find the pick point, and this pick point, envelope pick point, and then we try to know what kind of frequency range. So we try to know what's the frequency range. So they are dynamic range. You try to know what's the frequency range. So different phony will be frequency range a little bit different. So based on locating different frequency range, in traditional we try to understand your phony. So this one is the best idea. Why we talking about the phoneme? So first one, you have to understand pitch related to frequency domain. Pitch in time domain. Pitch is in time domain. And in frequency domain, we call the fundamental frequency. And then based on your frequency domain, we have your envelope. We can come out your envelope shape. So like this one, this figure. So you can see your envelope shape like a figure D, your envelope shape here. So you can see you have a big 500 here, 100, 1,000, 1,300, and 2,000, 2,300, and 4,000, 3,400 here. So you can see we try to multiply your pick point. So this one is related to your, sometimes related to your speech phonics information. So this windowing is 220. And then the other one, this window is we are called sample. So this one is supposed to be, this one is more like a speech signal on voice. So this one is a noise, more like a noise on voice signal. So we are windowing. We are not a rectangular window. So you can see in frequency domain, there's no harmonic structure. And then if we are using the noise on voice, we call on voice here. We are take the windowing, so you can see there's no harmonic structure here. So this one is a window sample is 220 here. And if your window is smaller, it becomes 40. So you can see your rectangular window. So they can contain more information. If you are using Hamming window, so you can see what they did. Most of them, what they did, most of them is like more like your format. So it's a harmonic shape format here. So once your window becomes smaller, so they are Hamming window because no big information, there's no big information inside there. So they will be in the frequency domain, they will be look like more simple. However, if you are using rectangular window, so they will be contain more detail there. But however, if you have because you have a boundary information, they have a boundary effect. So you are build up the model will be affected by your boundary. So will be make your envelope shape will be sometimes in frequency domain could be a little bit defaulted or affected by your boundary. We call this effect more like a leakage, because a Hamming window we are boundary smooth, make it smaller, close to zero. So boundary may not be affected by your transfer. So our transfer model is a model based on the central information. During the central signal at a central point, they have a relationship very clear their boundary signal. Based on their have a very clear relationship between the boundary signal, so they can build up the model more closely to original signal behavior. Okay, so this is some idea here. This one is a voice speech signal. Okay, so did you got it? So one of what we're talking about, what we're talking about here is more like we try to take the windowing while we are using Hamming window. Hamming window can smooth your boundary information during your build out the model, can minimize your boundary effect. Okay, I use the Mandarin. OK， 那这一章的开始呢，你可能要记住哈，我的语音所谓的 pitch 就是你的周期，那到你的频率 domain 呢，频率 domain 呢，实际上就是你的 harmonic， 也就是说 harmonic 这个每一个 harmonic， 这就是每一个 harmonic， 它的 harmonic 的大小的间距 delta f， 实际上就是你的 pitch 啊，就等效你的 pitch， 然后呢，在你的切音框之后，在你的时域轴、频域轴，你把所有的 waveform 的 peak 点，这个 waveform 的 peak harmonic 这些 peak 点加起来，你会发觉有个 envelope shape。这些 envelope shape 呢，我大概可以 model 出4个顶点。这个4个顶点呢，是之前语音处理在早期语音处理没有那么复杂的时候，最基本的，他们叫做声谱图，也就是说把声音切成一段一段。每一段都到频率，我把它的这个 peak 点的漂移度声谱图看出来。那声谱图看出来，实际上早期的基本音哈 R E V A O 或什么样的音 phony， 它的 phoneme 1、phoneme 2、phoneme 3、phoneme 4可能在的位置，他们语言学都已经做了 study。based on 这个，我可以做一个简单的音的辨识啊，这个是跟音的辨识有关啊。然后所以说课本在这里呢就有讲到。当你的音框越大的时候，当然你的资讯多more information， 那你当然可以建构比较完整的讯息。但是呢，如果你用的是这个是有声的无声的，所以说你看到频谱图的时候比较没有任何的 harmonic 讯号。那如果你是有声的，到频谱图比较会有 harmonic， 但是呢，你会发觉如果你是 rectangular window， 你的在频谱图上比较包含较多的细节，所以这2张图你说我看不太出来，较多的细节。那所以说，但是呢 ，Hamming window 会把你的 boundary smooth 到接近0，所以说呢，你在 boundary， 因为你的 Fourier transform 实际上就是换坐标轴，某种程度就是在原来的讯号想办法建构频率上的新的坐标的系数。那它在建构的时候，往往都是看你讯号之间的关系。那你周围的讯号突然像 rectangle， 突然这边周围的讯号，它看关系的时候建 model 的建 basis 的时候，发觉你的讯号不连续，就会造成我建的 model 不完全正确，因为 boundary 是变0了。那这边呢 boundary 缩小，它建的模型呢会比较根据中间有效的讯号去建立，周围 boundary 影响变小，那所建的内容呢比较接近原始讯号的特性，它基本精神是这个。那如果无声比较没好吗？那如果你要去看我的音框小一点，它的内容比较少，所以到频谱当然图会比较简单。所以从 V 跟 D 呢，你就比较容易看到，如果有 Hamming window。所以说相对的细节就少很多。那但是呢，我的 phoneme 1、phoneme 2、phoneme 3或许还有存在还有一些某种程度内容的存在。Okay. So right now, what we have to say, how to determine the window size, because what's the best window size here? So you can see what's a textbook comment or textbook comment. If Hamming window and rectangular windowing are still visible 4.6, 4.68 because their window size is smaller. So you can see they will be show different spectrum characteristics. So good temporal resolution require short window, while good frequency resolution speech require a larger window. So this one is straightforward. Why? If you try to get a good time resolution, so our speech signal more like this one. So if you try to get a good time resolution, so it's very straightforward. So our partition windowing, this one should be smaller. So our each time resolution will become good. But however, because small amount of data signal, small amount of signal to go through the frequency signal become the frequency. So you are doing the FFT. So their frequency information, frequency the resolution. So your time resolution increase. So your frequency resolution will be decreased. So you can see this figure. So our window become 40. So your frequency resolution become no good. But if your original signal window size become the 220 sample, so your frequency resolution become good, but your time resolution, windowing time resolution become not good because you are partitioning a bigger window. So this one is very straightforward. So windowing, so you can see independent, some attenuation, increase the length n, sometimes decrease the bandwidth. If n is smaller, so 40 sample, so your short time energy will be changed very rapidly. So they are modeled by very small window, so your energy will be checked, your signal variation will be tracked very good. However, because you are based on small volume of a signal, sometimes they try to build out a model is not precisely. It's not easy because data volume is too small. So n is larger, on the other hand, the older several pitch period. However, n is larger, your pitch could be changed. Your energy could be changed. So because you have built out a model, more like a take an average or try to find there some rule, some behavior, sometimes more like an average. So would be make the signal is not perfect represent your speech signal change property. What they want to say, because speech, you can see here our pitch will be some variation. So pitch will be some variation. So if we are windowing is bigger like this one. Windowing is bigger, but the pitch have some variation. We cannot, because we are doing the coding. So bigger windowing. In this windowing, we're using the pitch information data stream. However, if we are partition many small windowing, so our pitch information will be based on the small window to calculate the pitch. So we have a multiple pitch information. So their variation, so the variation can be tracked. So their time variation, we can do the tracking. So if you have bigger window, maybe inside the window they have a pitch a little bit change, or maybe the energy a little bit change. However, we are using a bigger window, so your energy, most of them take the bigger window, try to take more data to take the average. So that one cannot reflect some time variation. So this one is just show you if you are n is too large, so the older several pitch period may be short time energy will be energy over a long time, so they will be not property reflect the change probability of speech signal. So this implies there is no satisfied value n which can be chosen. So n small, so your short time energy is good, but your frequency resolution may be not good because we are trying to do the compression. We hope to make more data, based on more data to build out because inside the bigger window, our pitch a little bit change, and also our energy also be changed. So you'll be sometimes you'll be trouble there. So they say, well, there's no optimal end for speech processing. However, if we are consider physical meaning, like a female, they have a five female or children, like a child. So one pitch, so the minima could be 16. This one, your pitch period, the minima sum of guy could be 16 sample only. So they have a high frequency. So some guy for low frequency male, like a elderly, older guy, so they could be larger than 160. So it look like some speech signal is pitch is very short, and maybe some pitch signal this one is bigger. So this one, delta 2, they told you if you are a different person, like a children, this one, female children, so the pitch period could be down to 16 samples, so they have a high frequency. If it's very old male man, so the pitch could be up to the 160 sample. So it's a very low frequency response, very low frequency. So you can see, so if we are build out a model, we hope to cover our pitch information before we build out the model. Because we try to partition your signal by windowing. So after we take a Hamming window, so we hope to effect the information inside this window, speech frame. So sometimes your speech frame, the frame size could be 120 to up to 240. So 240 sample could be close to 30 milliseconds. This one could be 15 milliseconds, around 15 milliseconds, depend on your application. So because we try to do speech encoding, so we have to do some windowing, speech frame to cover sufficient information for us to build out the model. So later on, we have to build up the short-term prediction and long-term prediction. We hope the information, the speech data inside the speech frame are sufficient for us to build out the model. So they just tell you some physical meaning here. Okay. So I a little bit repeat the Mandarin. 那实际上这边在讲的一件事情是说，人类的语音有低频跟高，小朋友的女生呢频率可以很高，那它的 pitch 呢可以短到16个 sample。那如果是老年人呢，男生呢有可能他的 pitch 很短 ，pitch 很长，可以到160个 sample。那我们既然要切音框，希望把有效的资讯都含在这个音框里，所以说你不能短到连一个周期都没有，希望能包含一个周期。但是呢，在不同的应用，有可能 low delay 的 coding 它可能短到接近一个周期很短，那但是呢不容易也就是说它可能应用的考量，如果我是要为了做有效的高压缩率的 speech 的 coding。那正常一个音框必须接近包含有一个 pitch， 会比较好，让你建模型的时候。 所以一般来说大概10 millisecond 到30 millisecond，那是基本的精神是考虑到人类的周期啊，人类的周期有小朋友的女生16个 sample， 那老年人的男生可以到160个 sample， 这个大概是这个范围。Okay, so we are trying to know windowing, so speech windowing. So we have considered two issues. One is buffer delay. We hope to the human being did not perceive your speech communication based on the mobile phone. However, we did not see like a delay. So most of them should be more than like a 100 millisecond, 80 millisecond. But that one window could be too big, you know. So we are consider could be 30 milliseconds because they have an end-to-end delay. Buffer delay is just one of them. They have an encoding delay, transmission delay, decoding delay, and so on. So most of them will be speech frame will be considered 30 milliseconds, below 30 milliseconds. On the other hand, we are trying to find the one is from the delay, end-to-end delay perceptual point of view. The other issue is from because we are trying to do encoding build the model parameter. So we have to make sure our speech frame include sufficient information for us to do short-term prediction, long-term prediction like the pitch and so on. So this one is the main idea why they cover around the 15 to 13 milliseconds. Because human being, could be your frequency will be higher, so the pitch will be 16 sample. However, some guy will be very slower to say the word, so their pitch will be very longer. Like me, I will be say very longer. If you say very quickly, so the pitch will be shorter. So some guy could be up to the 240. So however, we are not covered. Sometimes we cover larger, sometimes we cover some of them, depending on your speech codec. So most of them we are considered speech frame. Some application down to 10 milliseconds. Some application up to the 30 milliseconds, depend on the speech codec. So the physical meaning, we try to do windowing will be around here. Okay, so next one we are talking about source filter model. So we try to build a model for our what we have to say because one most powerful speech analysis is a linear prediction analysis. So linear prediction analysis is more like a short-term correlation between the speech signal. Sometimes it's a format, a model, and removed by an efficient short-order filter. So we call this one is a linear prediction coding. Linear prediction coding is a short-term prediction process. So the latest speech coder, so we call this one is short-term prediction. In pitch, we call the long-term prediction. Why? So why is it called one is short-term prediction, the other is long-term prediction. So if you have speech signal like this one, so the short-term prediction, it looks like we try to predict this point. We are based on the neighboring sample. Try to do the linear combination. So they try to do the linear computation to predict the point. So you can see this one we call the short term. So they are short term prediction. Another one we call the long term prediction. So because this point also we can consider from the far away according one pitch. So this one based on that point or neighboring point, symmetric try to predict this point. So we call this one is a long-term prediction. So this one is a long-term prediction. Become the long jump step, long step size, long-term prediction. So they have a two word. Later on in this textbook, what we have to say like a pitch prediction, we call long-term prediction. If we are based on linear prediction is more like a local neighboring sample to do the linear combination. So we are trying to predict their next point. So this one we call that computation like a short-term prediction. So this one is what we say is a source filter model. Source filter model. So we have a trigger, we have a pitch signal, and then also this one is for voice. On voice is more like a random noise. So we have a gain here, and then they try to do some. Sometimes you keep silence, sometimes you have some voice. So they combine them together, and then we get a short-term prediction and come out a speech. So what they want to say here, because you have a pitch signal, is more like this one. So we have a pitch signal, maybe some variation. So this one will be delta 1, delta 2 is our pitch signal. And the other one could be some random noise, small random noise. So they will be combine them together, switching. So it's multiplexing, and multiply the gain. So what they have here, multiply the gain here. So they will be bigger, maybe the bigger. So different gain, different time have different gain here, and some signal will be small noise. This part is voice. This part is on voice, so they will be mixed them together, and later on they go to the time varying filter. Time varying filter will be short-term prediction. Short-term prediction will be normalize their signal here, will be do the normalization. Similar like this one. So this one what we call is a source filter model. This one what we call is source filter model. Simple source filter model. Okay, so sometimes this one is your pitch, but however, this trigger signal could be positive and negative. It's not always positive. Otherwise, you do not have a big variation. Okay, later on we show you after we finish what we said here. So right now we try to build out a model. So you can see S of n. So this one is output signal. So we have an output signal plus our input signal. So we are trigger. This one is our trigger signal. So this part is our black box. So we are trying to black box here. So this one is our transfer function. Okay. So this one is if you are if you are familiar with digital signal processing DSP, so that causes they will be tell you like a black box the transfer function. They will be from Z domain. This one is from Z domain. So this one is from Z domain. So you can define your transfer function. So this one is your transfer function. This one is your output. This one is your output here, and this one is your input here. Your input here. So you can get your transfer function. Transfer function. If you are trying to get the transfer function, you have a gain. So you have a 1 minus something. And also you have a pole here. This one we call the 0, some equal to 0. This one is sometimes this one is your pole here. So if we are consider your denominator, so this one is some polynomial equation. So we are right now we assume your denominator, the order, the order, the order of denominator. So we are trying to assume this order bigger than this one. For example, this one is like a maybe 1 minus z minus 1 minus z minus 2 z minus 3, and bottom one it could be z minus 2 minus z minus 3 and z minus 4 and z minus 5, like this one. So I did not write a coefficient. So the order in numerator in the back, this one is 3, this order is 5. So our denominator here, the order bigger than your numerator. So we are assumed they are order bigger than your numerator. We try to simplify the equation. So we try to simplify the equation. Simplify the equation. So we are trying to simplify the equation and then assume they are OPPO model. And then why we OPPO model? We try to make sure, because this 3 and this 5, something like that. So we are trying to some term delete, and simplify the equation, become the OPPO model, maybe just order by 2, because a denominator there are 3, numerator they are order of numerator, the order is 3, and denominator, the order denominator is 5. So maybe we can approximate the order OPPO model, just denominator by 2. So it will be, this 2 will be 5 minus 3 become the 2, because in original numerator they are order 3, denominator the order 5. We assume their equation can be approximate and deleted, and then we are denominator become the order become 2. We are simplify equation and assume our transfer function is an OPPO model. So based on this kind of assumption, so you can get your h of z become your gain, just your gain, and then only summation p, because this one is your z transform, hj z minus z, like this one. So you can see we are assumed they are OPPO model, like this one. So here, what this one is look like a linear prediction. This one is what we say is more like a linear prediction. However, this one is more general term. This one is an OPPO model transfer function general term. So you can see here for this one. So this one is our output related to our input here. So what we have is output versus our input here. So you can see this one multiplied by here, this one multiplied by here. So you can see we are reordering, become the time domain, here. So this one is in time domain is -1 minus z. So this one multiplied here in time domain become s of n. This one multiplied by this one in time domain will be g s of n. And this one multiplied by this one will be multiplied inside. Z transform will be delayed. So it look like, and then this minus will be moved to your right hand side. So you can see become summation p j equal to 1. So it will be aj s m minus j. So in time domain will be time index shift. In frequency, in z domain will be z power minus j. So you have to be familiar this fundamental mathematics. So you can see we are input signal, and then this one is our output signal. So our input signal will be trigger signal multiplied by gain, and then what's our output signal is based on their previous signal doing try to perform linear combination. You can see this one is linear combination. So is what we said before. What's the short-term prediction? So what's the short-term prediction? Short-term prediction is based on your you try to predict this point based on their neighboring sample doing the linear combination. So we are how to build? We are based on source filter model. Source filter model. Suppose we have an output. This is our input. We get signal. We hope we have a pole is not a zero. If you have a zero, make the signal become the zero. So that one is on voice. So most of them we are talking about speech is focused on open model, simplified. And then based on this open model, so you can see what we say, this one is more like a linear combination. So we are assume here if well-known linear prediction difference equation S of n. So we are summation a summing. So we try to do summing the present input data multiplied by gain, and also weighted sum the past output sample. So this one is more like a linear prediction. So and then you have a coefficient AJ. So that one is your parameter. So what's the P? P is your order, more like a look forward, look backward. Supposed to be look backward. How many sample your signal you are considered. So resulting parameter are assumed the parameter or model. So we try to get the best coefficient because right now what we say we have a speech signal. We have a speech signal here. So right now we are using the Hamming window. We are using the Hamming window. We are using the Hamming window. We try to build out the model. Right now we are start encoding. So what they want to say here, so if we have a speech signal here, and then we are trying to do the Hamming window. So you can get the signal. There will be smooth in the boundary. There will be smooth in the boundary. So they will be smooth in the boundary, and then so right now what we say we have supposed to be the number of friends will be n sample, and then we try to build out the model based on source filter model, so source filter model. So what's the source filter model is like this figure. So this one is our source filter model. Sorry, I didn't see in the beginning. So this one is our original signal. So we try to do the Hamming window. And will be smooth the boundary. And then total number will be sampled by n. So we are using the source filter, like textbook source filter model. And then we do some assumption, simplified assumption. We come out our signal will become our output signal will become your trigger signal plus your linear prediction. Linear prediction here, and then you'll be consider how to, because right now we are doing the encoding. Because we are trying to do based on source filter model, we try to do the encoding, try to build out how to encoding this signal, try to based on encoding. So you can see this is our trigger signal. These are recording speech. Recording speech. Based on this one, this is your S of n. This is your S of n. So we are trying to from S of n find what's the best. Try to find what's the best coefficient. Try look for the best coefficient. Okay, so they simplify the equation. They simplify here. They assume this one is smaller, close to 0. So we try to find from our speech friend, like a speech friend signal, try to find the best match, AZ. So we try to, our problem, our equation will become your S of n sum minus by your P, say equal to 1. And so we are not, they assume, here they are using alpha Z to represent AZ. So alpha Z is unknown. We try to figure out the value. So it will be Sm minus Z. So they will be based on your input signal. Try to find a best one, alpha Z, and then how to make it, how to make the error minimum. So you can see, because we didn't know which one is bigger, so most of them we are using the square. So you can see they are using the square. So our variable, this one is our variable parameter. So our variable parameter here will be, because we try to minimize this error function. So this one we try to make it, because we didn't know who is bigger, we can make it square. So we try to, because this one is our variable, so we can do the like a partial derivative. So this one is our E squared n. So we can try to partial derivative. So we can do the partial derivative like we have how many components we have, say 1 to p. So we can partial derivative by 1, partial derivative by 2, and that, and so on. So we have partial derivative by alpha p. So because we have a p component, we try to find the best one. We try to find the best alpha Z and make the lows become the minimized, become the lower. So you can see, because easy way, why? Because they are polynomial. This unknown value. So you can see they are tech square. They are polynomial equation order 2 and the positive. So they have a minimum. So we can, based on your variable, take the partial derivative. So based on you take the partial derivative, so you can, from equation 4.15 become the 4.16. So this 2 become here and then go inside there, inside term here. We try to take derivative, and then you can see only variable here. So it become here. So we have a p equation. So you can see the I equal 1 to p, and then you are change the symbol here. They define y phi n ij equal to the correlation, signal correlation. So original signal become here. So it looks like we are simplifying equation to become sub like a metric. So you can see we take the partial product, what we have here. So we take the partial product here, so you can see like we take the partial product, so you can see we have take partial product R1 and also partial like here, partial R2 and your arrow function partial RP. So if you take derivative partial R1, so what you have here, so you have 2 here, so become the 2, and then this order will be keep here. And then look into here. We are looking into here, and then we are variable only R1. So what is that? So only minus R1 will be take derivative. So that one R1 become 1. So that one will become as n minus 1. The other variable it is not related to R1 become a fixed value. So this one will be equal to s n minus summation p j equal to 1 of j s n minus j. Here is minus s n minus 2 and so on. So this one is easy. So you can see here what we have. The similar of j as n minus j, so as n minus p here. So you can see what we have here. So they combine them together. So they combine them together. So become the equation 4.16. Because they are polynomial by 2, so we try to minimize. So they are equal to 0, equal to 0, equal to 0. So we can get an equation like this one. So we are trying to say, put them together. So you can see how they put them together. So the older 2 is okay, it's constant. So we are not consider that one. So you can put them together. It looks like S of m minus summation p j equal to 1 alpha j s m minus j. And then you can see you have so many. So this one s m minus I. We hope to then to become 0. So your I, so this j is inside. We are talking about the I. I will be equal to 1 to p. Okay, so you can see if we are trying to make sure this 2 is orthogonal. So they try to make sure they are orthogonal. So your error will become a minimum. Deviation become minimum. So you can see here, if we are this one multiply inside and this one multiply inside, and reorder it. So you can see this one multiplied by this one. So you can see move to your right hand side. So this one will be Sn minus Sn minus I. On your right hand side, this one summation P j equal to 1 alpha j s n minus j, n minus j multiply. Okay, I rewrite it. So this one multiply inside and multiply inside, so you can get a summation p j equal to 1. So alpha j, so you s n minus j s n minus I, and then will be equal, multiply, move to the right hand side, so you can see Sn multiply Sn minus I, so your I is equal 1 to P, so you have so many. So you can see if we are define another symbol here, so this one we can say we are trying to use in this one, we are, okay, so we define another symbol here, we signal correlation, so you can see what we have, more like an equation, we can summarize equation like this one. And I equal to 1 to P. Okay, so if we are for example, your P equal to 10. What you have? So you know like a metric calculation. So what's the metric calculation here? So this one, for example, P equal to maybe P equal to 4 is easy. P equal to 4. What you have? What do you have here? This equation can become, so P equal to 4. So this one, I also equal to 4. So what you have? So you'll be R1, R2, R3, R4. So you'll be Yn 1, 1, Yn, well, too small. You'll be Yn 1, 1, Yn 1, 2, so Yn 1, 3, and Yn 1, 4. So you have a Yn 4, 4. So this one is your R1, R2, R3, R4, and your right hand side will be Yn 1, 0, Yn your Yn 1, 1, 1, 0, 2, 0, Yn 3, 0, and Yn 4, 0. So you can see what's the Yn. Yn 1, 0 is a signal correlation. So one is have a shift, no shift. The other is shift 1, shift 2, shift 3. So this one is our signal correlation. And this one is your unknown information. However, here is also signal correlation. So we can do the metric inverse. Metric inverse to get your best R1 to R4. So you can get it. So you can see what we have to do. We try to calculate our short-term prediction coefficient is based on inverse your metric. So you can see it's very straightforward. What we did before in the beginning, what we did. So in the linear prediction, we try to get based on this input signal, what's the best match coefficient? What's the best match coefficient? So we are trying to make this one trigger signal is close to 0 based on original signal and based on your previous signal. So we are trying to build out the model, and then we are trying to get what's the parameter alpha z. So because our variable is alpha z, so we take the partial derivative here. So if we are partial derivative, we have a p partial derivative, so we can reorganize here. We assume they are equal to 0 because they are second order polynomial function. So they have a minima because second order they are positive value. So we are reordering. So you can see how to get your coefficient. The best coefficient is how to get your best coefficient is more like a solve your metric equation. Okay, so I using the Mandarin 这边在讲的是 short-term prediction。那 short-term prediction 一开始呢是介于我原始的讯号，我用了 Hamming window 把 boundary 变小。我需要在这里面讯号建我的 short-term prediction 的模型。那我的基本精神是一个 source filter model， 我有一个 trigger signal， 加上我用之前的讯号做线性组合，产生我现在的讯号。那这个呢是原始的 transfer function 里面，假设它是一个 OPO model， 分子没有 Z transform， 假设分母的多项式的 Z transform 的多项式大于分子的多项式，这个之后会讲。物理意义，然后假设是这种现象的时候，我就可以假设它的分子的 order 可以被我的分母 order approximate 消掉，只剩下分母的 order。 那这时候的式子就会简化成这样，原来的 transfer function 啊，也就 input output 的 transfer function。Based on input output transfer， 我的变数是这个 AJ， 就看你要用多少个前面的系数做后面的相邻的一个信号做预估。那我的变数有 P 个，我就对 P 个做偏微分，因为我的 arrow function 是这两个相减 ，S of n 就是我原来 Hamming window 所得到的讯号，这是已知。那未知是 alpha j，unknown 是未知是 alpha j。那我把它做平方，实际上 alpha j 的它是二次式的平方项，这个平方后是为正，所以说它有极小值。我对它做偏微分等于0，实际上就可以得到我的极小值的条件。那我有 P 个条件，我把它组合起来变成是这样，然后把这个式子乘进去，重新 reorder， 那你就会得到类似这个式子。那这个式子假设 P 等于 4， 你的展开会是怎样？展开就变成是这个矩阵。这个左边这个矩阵实际上就是你的S of n 的讯号的不同移位的 correlation 的矩阵，跟右边也是一个有移位，一个不移位的 correlation 的值，那去解反矩阵求解，就得到你的最佳的预估系数 short-term prediction 系数。所以说基本精神是这样。Okay, so what we say here today, we are trying to give you some idea. First is a Hamming window is popular use in our speech processing, and second, the window size is not which size is good, but in our application we are consider resolution, time resolution, frequency resolution. Most of them sometimes consider sufficient information inside the speech frame, could be 15 milliseconds to 30 milliseconds. And then we are source filter model, and then our model is an OPPO model, no zero. So based on this kind of condition, we can come out coefficient. And then this one is our linear prediction coefficient. If you are based on source filter model to do the linear prediction, so after the derivation, after your computation, is look like a matrix inverse. So if you are P equal to 10, so your matrix is 10 by 10, and then this one is 10, and then this one is 10. So depend on how many coefficient you are doing the linear prediction. So this one is what we say is a short-term prediction is based on linear prediction. Okay, we stop here. You have to prepare your homework 1. So next week is our homework 1 presentation. So TA will be set up the presentation time, and then maybe we are using Skype, and sometimes some students not available to read what you present. So maybe I will be asked the TA to do some recording and also to upload our e-course for you later to do the reference. So because some foreign students didn't understand Mandarin, and Mandarin students maybe not give a good English talking. So some students could be using Mandarin. I will be do the translation later. And also some foreign student could be you are using it's supposed to be should be using the you do the presentation by English. So later on I will be a little bit comment by Mandarin for our domestic student. So talk to you next week. Okay, we stop here.